Bismillahirrahmanirrahim. We will going to study sum of product expansion of the Boolean function. The sum of product expansion of the Boolean expansion is also called the disjunctive normal form of Boolean function. And as we have learned in the previous video that the function can be expressed through its min terms. So if we have some Boolean function and we are able to write the min terms of the function, right, where the function gives the output 1. So the min terms are the terms where the function gives the output 1. So for example, this function gives the output 1 at x is equals to 0. So we write x bar, y and z bar. So y is 1, so we write y, and z is 0, so we write z bar. Similarly, this term, this one of f can be represented as x, y bar, z bar. And this term is represented as x, y, z bar. So these three min terms are sufficient to express f as the Boolean function if we sum them together. So we can write f x, y, z is equals to x bar, y, z bar plus x, y bar, z bar plus x, y, z bar. So this sum of product is called sum of product expansion or disjunctive normal form. Why? Because it is expressed in the sum of the min terms. So every product is not sum of product expansion. For example, if we directly apply distributive law over this function, then we get x z bar plus y z bar. So this is also a sum of product, but this is not the product which we require in sum of product expansion. We require a special kind of product which is called the min term. So if we write the function in the sum of the min terms, then only we say that this is a sum of product expansion of the function. And what are the min terms? Min terms are those terms which indicates the truth value of the function is equals to 1 in the truth table. So in the sum of product expansion of this function, this points out clearly that there are 3 rows in the truth table where the function has value 1. The first row is where x is 0, y is 1 and z is 0. The second row is where x is 1, y is 0 and z is 0. And the third row where x is 1, y is 1 and z is 0. So this is the sum of product expansion. So we can write sum of product expansion of any function. For example, in this example, we are given two functions f and g with the help of this truth table. So this function f is 1 at only one place of the truth table. So the sum of product expansion of this function can be written by just only one term, which is x, y bar and z. Similarly, this function g is 1 at two different places. So we write the sum of product expansion as x, y, z bar plus this one x bar, y, z bar. Now the sum of product expansion can be written with the help of truth table. That is, if the truth table of the function is given, then we can write the sum of product expansion of the Boolean function with the help of the truth table. But if the function is given in this expression form or Boolean expression form, then we can also identify the sum of product expansion of this function by applying Boolean identities. For example, this function is equal to x z bar plus y z bar by distributive law. And now, since these are the sum of product, but it is not the sum of min terms, therefore, in order to make it min term, we introduce the variable which is missing out there. So in this term, you see that the variable y is missing, and in this term, we have variable x is missing. So we apply the identity law by multiplying 1 in between x and z bar, and here in the place of x, we multiply 1. So this is unit property or identity law, or unit property. Now in place of 1, we insert that variable which is missing. So here y is missing, so we write y plus y bar instead of 1. So this is negation law. So again, here x is missing, so we write x plus x bar instead of 1. So this law is negation law. Now again we apply distributive law to get all the terms expanded. So now we identify the like terms. So these two terms are like. So we apply domination law, idempotent law, to combine them together, and we get x y z bar plus x y bar z bar plus x bar y z bar. So this is distributive law, and this is idempotent law. So now this function is written in the sum of product expansion. So this is sum of product expansion because this is written in the sum of min terms, and every variable's representation is present in each of the product term. So this is how we can transform a function in terms of sum of product expansion by using Boolean identities. So from here we identify immediately that this function is equal to 1 at the three different places of the truth table. Now if the variable is of three, if the function is of three variable function, then there are total 8 rows in the truth table, and the number of rows represent how many number of min terms will represent how many rows will get value 1. So if there are 3 min terms available in the sum of product expansion, then the truth table have 3 rows which have output 1, and if there are more min terms available or less min term available, then the values of the output of the function will differ accordingly. So this is another example from where we can write the sum of product expansion of the two functions f1 and f2. Here you see that f1 is 1 at 3 different places and f2 is 1 at 5 different places. So we can write the sum of product expansion, and each sum of product expansion of f1 contains the 3 terms and f2 contains 5 min terms. Now there are some other complex functions which are given to write the sum of product expansion by using the Boolean identity. So we will do few of for those, and rest of the ones are exercise for you. So I first solve this first question by applying Boolean identities. So first of all, I convert this conditional in the form of plus and negation. So this is equal to negation y or y bar plus x into x bar y. Now we apply distributive law to get x bar y bar. This term is multiplied by this plus x bar y. So y into y bar is 0 and x into x bar is also 0. This is the negation law. So this becomes 0. So what does the 0 mean? 0 means in Boolean algebra that the function is identically equals to 0. It means that it doesn't give output 1 at any place of the truth table. So there are no min terms or the sum of product expansion that could represent this function. Now let's do this third function. So again we convert this implication into the simple operators. So we write x bar plus y plus y bar plus z. So let's apply double negation law and we get x plus y plus y plus z. Now by using associative law and idempotent law, we get y plus z, and again by associative law and idempotent law we get x plus y plus z. Now this is the sum of 3 terms, but it is not sum of product expansion, so we introduce the missing variables. We multiply it by 1 and we directly write it y plus y bar, z plus z bar plus x bar times y into z plus z bar and plus x bar y plus y bar times z. So now apply distributive law, we get x y z into x y z bar plus x y bar z plus x y bar z bar, and from here we get x y z plus x y z bar plus x bar y z plus x bar y z bar, and from here we get x y z plus x y bar z plus x bar y z plus x bar y bar z. So now we add up the like terms. So xyz is here, xyz is here, and xyz is here. So by applying idempotent law, we can write it just one xyz. Now xyz bar is here, xyz bar is again here, and that's all. So again by idempotent law, we write xyz bar plus xy bar z. So xy bar z is here and here. So we get xy bar z, and now we have xy bar z bar. So we have xy bar z bar is only one, xy bar z bar, plus we have x bar yz. X bar yz is here and here, so we write x bar yz, and now x bar yz bar. So we have x bar yz bar and x bar y bar z. So there are 1, 2, 3, 4, 5, 6, and 7 minterms in this sum of product expansion, which means that in this 3 variable function, if we represent it with the help of truth table, then the 7 rows have output 1 and only 1 row has output 0, and the row which has output 0 is the one where all the 3 switches x, y, z are 0 or off. So it means that it represents the extended or simple or of 3 functions x plus y plus z, as you can see this from this line also, that it is just the or of the 3 switches. So this complicated function can be written as in a simple way as x plus y plus z, and from this sum of product expansion it is more clear that this is representing an OR of 3 switches. Similarly, we can do the other examples, other problems which are given in this slide. So these are left for the exercise. So now we can also construct the circuit of the light fixtures, which represents certain Boolean function. For example, this Boolean function which has output is equals to 1 when both the switches are on, and the output is 1 when both the switches are off, can be represented through this Boolean function. Here you can see that output 1 gives us that when x is 1 and y is 1, which is represented by this minterm, and both are 0 is represented by this minterm. So x bar, y bar. Also, it must be very clear to you that x by y bar, xy whole bar is not equal to x bar y bar. So there is some misprint when we are combining this. This means that we applying De Morgan's law and it becomes x bar plus y bar. So we always used to write x bar y bar independently, separately bar, not the whole bar on the same product. So this is how we can write the sum of product expansion, and we can express this sum of product expansion with the help of the circuit. Similarly, we have another word problem. You can see that again this is the problem to design a circuit for a porch light, and the porch light P depends upon the 3 things. The first thing is that it is dark, and the second thing is a motion sensor detects a person in the front yard, and the third one is the switch is on. So if we represent D with the switch, which represent D, it is dark, and M represent the motion sensor, and S represent the switch, then this porch light is a function of 3 variables, which is D, M, and S. And if we translate it logically, as we have studied in the propositional logic, then it is written that it is D and M. So we write D and M or S. So or S. So this is how we can sum up it with the help of the propositional logic. And if we want to write it or express it with the help of truth table, then you can always construct the truth table with the help of three switches D, M and S. You can take it any variable x, y, z instead of D, M and S, and this P porch light can be taken as F, and you can see that this Boolean function becomes 1 when either these two are 1 simultaneously, so D and M both, or S. So D and M both, and this is 0, and D, M and both, and this is 1. This is 1 and this is 0, but this is 1. This is 0, this is 1, and this is 1. These both are 0 and this is 1. So in these 5 rows, this function 1 will gives the output 1, and in the rest of the rows it will be output 0. So we can again write the sum of product expansion of this function like D M S bar plus D M S plus D M bar S plus D bar M S plus D bar M bar and S. So this is the sum of product expansion of the given function. So in the next class, we will study about the minimization of the circuit. That is, we have a circuit, we have a problem, and we identified the sum of product expansion. We can construct the circuit, but now we want to minimize it. We want to use as less the circuit component as possible by taking the minimization of the circuit, and this will be done with the help of